Так, ну, хорошо, можно и по-английски. Okay, it's possible to speak English, but first of all, I'd like to understand whether you know something about graphs. Since if you know a lot about graphs, of course I can show you this presentation. It's hard enough. It's not introductory in some sense, but maybe introductory, so I don't know. Is it possible to hear me in Zoom as well?
Yes.
I'm absolutely sure everyone here hears me, but in Zoom, yes, okay. So first of all, what do we know about graphs? Do you know just the definition of a graph? What is a set of vertices, a set of edges, or not? Okay, but do you know, for example, that graphs may be simple and maybe not simple? If we say a graph is simple, we understand we mean that it doesn't have loops. Let me write it down on the whiteboard. Just a second. So if you have a vertex and such an edge, then your graph is already not simple. This is called loop. Okay. Also, if you consider only simple graphs, you don't assume multiple edges. So this situation is also forbidden. Yes? My English isn't understandable. I can translate into Russian if necessary. Of course, for me, it's much better to speak Russian, but I'm trying to speak English also enthusiastically. So what's about the third how to say, restriction? In simple graphs, we don't have directions. This is also forbidden. So probably in this first lecture, I'll consider only simple graphs. Okay, let's try to look at the presentation now. Okay. It doesn't want to work.
Надо нажимать несколько раз или проще.
Oh, now it works. It's necessary to make much more pressure. Okay, a general definition. Okay, graphs on n vertices. So let's fix a set of vertices. For example, a set of n natural numbers. Is it okay to have a set vertex just numbered by the first natural numbers from 1 to n? So it's a finite graph, of course. We don't consider infinite graphs now. Okay. And let's consider the set omega consisting of all possible graphs on n vertices. I mean simple graphs. Here in the presentation, it's also written down about simplicity. What is the cardinality m of omega? No, it's a good question for introductory lecture. How many graphs do we have on n numbered vertices? If the vertices are numbered, how many graphs do we have? Yes? No, it's closer than n factorial, but also not true. Not 2 to the power n. This is for Zoom listeners.
We're talking specifically about simple graphs.
We talk specifically about simple graphs here. It's also written down. Of course, it depends on what you mean by a graph, and we consider only simple graphs, and this is an answer for my question. It's already here. So how to explain it? Of course, if the vertices are numbered, then, for example, this graph, 1, 2, 3, 4, and this one, which is numbered, say, 1, 3, 2, 4, this way. These are different graphs. You understand it? Since here you have, say, an edge 1, 2, and here you don't have such an edge. This is very important. They are, of course, isomorphic. You know this notion, isomorphism of graphs. The same form. But they are different, since here there is no edge, 1, 3, and here we have it. So these are different graphs. And if you consider the set of vertices from 1 to n in general, then of course for simple graph, the maximum number of edges on this set of vertices is equal to n choose 2. Yes? The matrix is also simple, like graphs. The number of all possible unordered pairs on n vertices is n choose 2 by definition, which is of course equal to n times n minus 1 over 2. It's possible just to calculate the factorials here, and this is very simple as well. So this is the number of edges in the so-called complete graph on n vertices. And every edge in the complete graph on n vertices may be drawn and may be not drawn. Yes, so 2 variants for every edge. And this means that the number of all possible graphs in this way is exactly 2 to the power n choose 2. Okay? What's about the speed of my formulations, my English? It's okay? Okay, fine. So, what I want to speak about is the following, how to say it, the following concept. In fact, it's very useful to consider different properties of graphs, of course. And you know a lot of properties probably, but I'm not sure. So let's discuss which properties of graphs do you know. For example, do you know what is connectivity of a graph? Please, поднимите руки. Связность. What's about connectivity? A lot of people don't know, but not everyone. So let me say a few words about connectivity, since this is, of course, one of the most probably important practical properties of graphs. So it's possible, of course, to make different paths in the graph. And sometimes it's impossible to go from one vertex to another one just by considering a path. So if it is impossible for some two vertices, then the graph is not connected. And if it is possible to do so for every pair of vertices in the graph, then the graph is connected. So for example, this graph is of course connected, but you may consider both such graphs, for example, 1, 2, 3, 4 here, and 5, 6, 7, 8 here, and not draw any other edge. So this graph consisting of two parts is called not connected, and it has two connected components. Две связанных компонента. Two connected components. Okay, but for example, if you draw this edge, this graph becomes connected. So this is connectivity. Which other properties of graphs may be proposed? Maybe you can propose some property which you know, which you think to be important for science. I don't know. You have some specific interests here, so probably you are interested in some specific properties of graphs. No, connectivity is of course very important, but maybe something else. Do you know? Oh, chromatic number, it's fine, it's fantastic, but yes, I understand why you tell us. Yes, I'll speak about chromatic numbers, okay? Which?
Number of clicks.
Number of clicks, or the maximum number of vertices in a click, for example, yes? So I'll speak about all these notions in this lecture and maybe tomorrow as well. Okay? What is a chromatic number? I'll tell you a little bit later. But the concept here is not only to study different properties. It's also important to understand how many graphs to have a property, which is interesting for you, for example, connectivity, and how many graphs do not have this property. And in this case, it's very important to use probability theory. So it's very important not only to consider graph-theoretic properties like just consider a graph, whether it has or not doesn't have a property. It's also important to understand how many graphs in some probability theory measure how many graphs to possess such a property. Do you understand the question? So I have to define what I mean by a random graph, and this is very important for many, many different applications. Okay. 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 Okay, fine. A random simple graph on inverses, what it is. Of course, what is first coming into mind? Maybe you have also some suggestion. Okay.
You have inverses and you place edges between them randomly with some probability.
With some probability, yes. Yes, yes. Binomial random model is more specific case of this, yes. But first, I think first coming in mind is the following very simple definition, which is of course not very general. Just a second. Just to consider all possible so many graphs and take every one randomly with uniform distribution. Just say you have a box consistent of so many graphs, and you just take randomly one graph from this box. It's a particular case of a binomial model, but I'd like to speak about it later. A much more general definition is, of course, given here. So it's possible to assign to each graph on vertices. We have so many graphs. So we have graphs G sub 1, G sub m, and we just can assign a probability P sub I to a graph with a number I. Of course, the probability must lie in a segment 0, 1, and the sum of all probabilities must be equal to 1. This is written down here. Yes? Is it okay? If something is not, how to say, if you don't understand something, if you have questions, if you have, I don't know, doubts, then of course, please let me know as soon as possible. Since in Russian it's called koknut. Я не хочу koknut. I don't want to kill you during this lecture. I don't know how to translate koknut into English, but kill is something like that. Huh? Of course, here we have a flexible model. So we can assign a probability in such a way that this will be used in applications, for example. So you have some concrete graphs in the real world. For example, you have internet, World Wide Web. Or for example, you have transportation network consisting of roads. Some cities are connected by the roads. And depending on the properties of your real world network, of course, you try to assign these probabilities in such a way that after that, the random graph defined by you with high probability has the same properties as the reality. So it depends. It's already another case how to assign the probabilities. But now we will define some concrete probabilities, binomial ones, and we will study this more. Different properties for this one. Okay. Just a second. Okay. So this is called classical ANDREI binomial model. Don't kill me for ANDREI. I'll explain why it's called so a little bit later. So the main definition here is the following. Let's consider again the set of n first natural numbers as the set of vertices. And assume that each of n choose two edges of the complete graph on n vertices on these n vertices is drawn independently from each other with the same probability p, the same probability for each edge. Okay? What is the probability of a graph? It's written down here, but probably it's better to ask you. So, for example, consider this concrete graph on 4 vertices, n is equal to 4. Okay?
We could take the number of edges, this graph, p in this number, and 1 minus p for the rest.
Yes.
No,
You saw the same, yes? Okay, it's good. Since almost every time I get an answer 1 over 16 or 64. 1 over 64 is not true, provided, of course, p is not equal to 1/2. If p is equal to 1/2, yes, this is 1 over 64. 1/2 to the power 6. But in general, it's written down here. Of course, it's natural to assign to a graph G the probability which is equal to p to the number of edges of this graph, of this concrete graph here, it's p to the 4, and times 1 minus p to the number of non-existing edges, not drawn edges. Like here it's 1 minus p to the power 2, okay? Is it a correct model? What do I mean by a correct model? I mean, of course, we have to understand whether the sum of all possible probabilities here is equal to 1. Intuitively, this is of course okay, since if all the edges are drawn independently, then of course we multiply the probabilities, yes? So we have multiplied the probabilities, and this is intuitively true. But anyway, we have to understand whether the sum of all possible graph probabilities equals 1. Here it is written down. So is it possible to understand such a big formula? You see here a very interesting binomial coefficient is written down. 1 choose 2, choose k. Is it not killing? No? So we take all possible ways of drawing k edges from the set of all possible n choose 2 edges of the complete graph. This is the number of graphs having exactly k edges, yes? Or not? Killed? Около? Около, да? Ой-ой-ой.
Describe this phase.
I'm trying to discuss it as easy as possible, but I can do it even easier. So if you need, I have to explain it here on the whiteboard. It's not very difficult. Just a second. This is. You see, this is an introductory lecture, so I have to be understandable by everyone here. If you don't understand me, please stop me. So this is the set of vertices. Yes? This is the number of all possible graphs. Vertices, this was understandable. Now I take this. So this is n choose 2. The number of all possible edges of the complete graph on this set of vertices. We can say denote the edges by e sub 1, e sub 2, e sub n choose 2. It's okay. This is some enumeration of all possible edges of the complete graph on this set of vertices. Yes. Okay. Now we have to understand how many graphs with exactly k edges do we have. We just take all possible ways of taking from here k edges, the number of edges, the total number of edges is n choose 2. So the number of ways for taking k edges It's exactly this one. Is it better now? No. No. Of course, this number includes non-connected graphs. It includes connected graphs. All possible graphs with k edges. Huh? Is it understandable? Huh? Please. Or hands. No. You will see some theorems which are very, very beautiful, but very difficult. So let me be understandable right now. Okay, so if you understand it, okay, it's very good. Now the sum of all possible probabilities here is the sum over all possible values of k from 0 to n choose 2. And here we multiply n choose 2 choose k by the probability of every graph having exactly k edges. Of course, the probability of every graph with exactly k edges is p to the k 1 minus p to the n choose 2 minus k. And this is, of course, a binomial formula, p plus 1 minus p to the power n choose 2. I think this is also understandable. And this is, of course, equal to 1, so the model is correct. If we speak about the reality which is under this model, for example, we may have such an intuition. We consider some computers located in different cities in the world or in different cities in Russia, for example. Some servers, some computers, a lot of different computers. The total number is equal to n, of course. This is the number of vertices in our graph, but now the vertices are such computers. And in the beginning of picture, every two different computers have some specific connection between them. So it's possible to transfer some information from this computer to this one. It's possible to transfer independently some information from this server to this one, from this one to this one, and so on. So we have a complete network of all possible connections between these n computers. The network consists of n choose 2 edges connections. And now we assume, and this is absolutely natural, that there exists some probably adversary противник. Or this is just some, I don't know, some random case. So of course it's possible that a connection is broken. Yes? It's absolutely possible that the connection is broken. Let's assume that the probability of a connection to be broken is equal to 1 minus p, where p is in turn the probability of the conservation of this connection. So p is the probability of this edge, and 1 minus p is the probability that this edge is not drawn. And it's also absolutely natural to assume that such breaks appear independently of each other. So we have exactly this model which is depicted here on presentation. Yes? Yes. Okay, fine. But for example, if we speak about such networks as social networks or internet, of course, this intuition is not very good. So binomial model is much, much better for such practical cases. But for different practical cases, it's important to assign to a graph an absolutely different probability. So you understand, yes? В разных ситуациях нужно по-разному рисовать. But it's a very good and very beautiful model. So it's much simpler than many others. This is also very good. So of course you understand now the reason why this model is called binomial, since we have here binomial formula. Also it is called, it's named after ANDREI and RAIGORODSKII. The physicists do not like this name since they are absolutely true. Much before ANDREI and RAIGORODSKII studied this model, it had been a lot of different results about it. So ANDREI and RAIGORODSKII were very good in promoting this model. They produced a lot of important results in 1959 and 1960, 1961, and after it, a very intensive mathematical study of this model began. So that's why we also call this model ANDREI and RAIGORODSKII. But if you don't like it, let's just call it classical binomial model. Okay. Oh, do you remember the chromatic numbers? Some one of you proposed to study them, not only connectivity. This is also a very important property and notion concerning random graphs and graphs. Okay, here is a definition, but I'll show it also on this whiteboard. Chromatic numbers. Okay. What is the chromatic number of a graph? It's the smallest number of colors needed to paint all the vertices. Each vertex receives some color in such a way that the number of colors is minimal possible, and the endpoints of every edge are of different colors. Okay? Maybe here something more. It's impossible to have an edge with the same colors, but you may use different colors, the same colors for different pairs of vertices which are not connected. Just a second, I'll show you. So actually, you just take the set of vertices of your graph and you try to divide it into non-intersecting parts, say V sub 1, V sub 2, and so on, V sub high. By this sign, I mean that the union is disconnected, so there are no intersections between the parts. And for every part here, for every I, we suppose that every two vertices lying in V sub I are not connected by an edge. There are no edges with vertices of the same color. This is colored 1, this is colored 2, this is colored high, so we have high colors. And we assume that every two vertices of the same color are not connected by an edge. If you have an edge, it has one vertex in one part, in one color, and the second vertex in some other part of a different color. And high of G, the chromatic number, is the minimum possible high. So from practical point of view, how to understand what is the chromatic number of a graph? For example, let's assume that people sitting here in this audience are vertices of a graph. And let's, for example, connect two people by an edge. If for some reasons it's impossible to put these two people to one room in a hotel, for some reason, I don't make it concrete. I don't know for which reason. So the chromatic number of this graph, what it is, it's the minimum number of rooms which can be used in order to locate you in a hotel without conflicts. Yes? You color, this is one room, there are no conflicts, no edges. The edges are drawn if there is a conflict. This is the second room, this is the last room, and we need the minimum number of rooms to locate you. Maybe not in a hotel, in a dormitory. В общежитии. Okay, so this is a very important notion of graph theory, which is of course used in many applications. For example, not such applications, but you may consider some industrial, some industry, and you have a computer which tries to calculate every processes which are being used in this industry. And sometimes the computer cannot calculate two different processes, since this is too difficult for it. Ну, слишком сложно сразу два процесса обсчитать, он ломается. It's broken after trying to calculate simultaneously two different processes. So we have a graph whose set of vertices consists of all possible properties of, of all processes, of all possible processes. And two vertices are joined by an edge if these two processes cannot be calculated by the computer simultaneously. So the chromatic number of such a graph is the minimum number of, how to say it, feedings to the computer. Сколько раз скормить ему? Это задача, чтобы он все порешал. To be solved completely. How many feedings to be solved completely. Okay. Unfortunately, the calculation of the chromatic number is a very hard problem in terms of algorithms. So for every graph, it's very difficult, very hard to calculate the chromatic number. But for random graphs, it's possible to solve it somehow. Do you understand what I say? Maybe even some examples. Let's consider a simple cycle on n vertices. By a simple cycle on n vertices, I mean just a polygon in some sense. Here we have n vertices. What is the chromatic number of the cycle? If you understood the notion, you okay? Two? Every time two? Yes, sure. The chromatic number of a simple cycle depends on the parity of n. So it's equal to 2 if n is even, and it is equal to 3 for every odd value of n. And for example, if you consider a tree, do you know what's a tree on n vertices? A tree is an acyclic connected graph, yes? A connected graph which doesn't contain any cycle. What is the chromatic number of a tree? Almost every time, but there exists such a very simple tree. Just one grain. Its chromatic number is of course equal to 1, but in all other cases it's equal to 2. All right. So okay, now we understand the notion. I'm sure, absolutely sure. So let's proceed here. Here I want to speak about some simple results concerning a random graph. What is the chromatic number of a random graph? But of course, it depends on what is P, the probability of an edge, yes? And actually, for many different applications, it's very important to have P not a constant for all possible values of n, but a function which depends on the number of vertices. Okay. It's important. So the first and absolutely simple case is depicted here. If P of n, the probability of an edge in the binomial model, tends to 0 as n tends to infinity with a very high speed, which speed? P times n squared even tends to 0. So P is little o of 1 over n squared. О маленькое, да? Все знают, такое маленькое. Little of 1 over n squared. In this case, asymptotically, almost surely, it's an official definition of this triple word. Asymptotically, almost surely, the random graph in the binomial model doesn't contain edges, and so is, of course, one colorable like in this case. Why it doesn't contain edges? Let's try to understand. Yes, but what is the probability of not having an edge? 1 minus p? What 1 minus p? To which power? And choose 2, of course, yes. This is the probability that a random graph doesn't contain any edge at all. Yes? No edge in the complete graph on the vertex is drawn. But this is, of course, greater than or equal to 1 minus p times n choose 2. Do you know this inequality? Bernoulli inequality, yes, this is called Bernoulli inequality, very simple inequality, which is known maybe for even some high school students. This is, of course, 1 minus p times n minus 1 over 2. This is asymptotically n squared over 2, but p times n squared goes to 0 by our assumption. So this subtraction goes to 1 as n tends to infinity. So with very high probability, with probability tending to 1 as n tends to infinity, there are no edges, and so the graph is just one color. Okay? Now a little bit more complicated property. Oh. Now let's assume that p goes to 0, but not so quickly probably. Probably as quickly as in the first item, but probably a little bit slower. Yeah? P times n goes to 0, but maybe p times n squared already doesn't go to 0. P is little o 1 over n. I formulate here the result. So I say that asymptotically, almost surely, with probability going to 1 as n tends to infinity, the chromatic number is less than or equal to 2. Before we try to prove it, please show me your hands if you know the notion of a bipartite graph, двудольный graph. Not everyone, okay. This is very important since, in fact, a bipartite graph, people, is the same as a graph which has chromatic number equal to 2. But usually it is defined in a different way, which is of course equivalent to what I just said. So bipartite graph, it's a very important notion of introductory graph theory. Bipartite graph.
What is P of n?
The probability of an edge. We defined a binomial model. Remember? Okay. again. Oh. Now you see here P from the segment 0 to 1. Oh, oh just a second. Oh, this one. This was the probability of an edge. We draw each edge independently of each other with probability P. This was a binomial model. Hopefully. I don't understand what is the question. Everyone understood this. I thought, but now I understand you didn't understand. Now I see. You probably didn't understand it. So I spoke about computers linked by some connections. There was a picture here about computers located in different cities, which were pairwise connected by some connections. So there was a probability 1 minus P to kill an edge, and a probability P to keep this edge. No, if you want to have a formal definition in terms of probability theory, you know such a notation. No? You speak about probability events. Do you know that in probability there is a space of elementary events, some algebra of different events, and a probability which is assigned to every event in the algebra F. Yes, you know it. So here omega consists exactly of all possible graphs on the set of vertices consisting of an first natural numbers. There was such notation on the previous slide. Omega is exactly the set of all possible graphs. The cardinality of omega, which was denoted by m, is exactly 2 to the power n choose 2. N choose 2, sorry. This is not a n choose 2. Yes, this is not a fraction. This is n choose 2. This is the set of all elementary events. Every graph appears as an elementary event. And an event here, F, consists of all possible sets of graphs. So, for example, a set of connected graphs is the event that you got a connected graph. Но дайте я по-русски скажу, так будет понятнее. У вас есть множество всех графов на n вершинах. Вот всех, вот он. Множество графов на n вершинах. Каждый граф может реализоваться или не реализоваться. Вот еще на предыдущем слайде, но в самом общем виде говорили, что можно вот так вот определить каждому графу, просто приписать численку, которая означает вероятность его возникновения. Вот здесь вот написано. Все графы перенумеровали и каждому приписали какую-то численку. Теперь мы говорим, вот конкретная биномиальная модель. Мы делаем так. Мы предполагаем, что каждое ребро из вот этих c из n по 2 штук появляется независимо от остальных с вероятностью p. Поскольку ребра появляются независимо, то мы вероятности интуитивно перемножаем. И говорим, вот оно определение вероятности конкретного графа. Есть конкретный граф с этим множеством вершин и каким-то множеством ребер. Вот мы ему приписываем интуитивно понятную вероятность. Мы перемножаем столько p, сколько в нем есть ребер, и перемножаем столько 1 минус p, сколько в нем нет ребер. Пример у нас был конкретный с 4 вершинами, цикл на 4 вершинах. Вот у него вероятность p в четвертой на 1 минус p в квадрате. А дальше мы проверяем, что так приписанные графом чиселки, они действительно обладают нужным свойством. Сумма равна единице. Вот это биномиальная модель. Но p может зависеть от n. Для каждого n вы вольны брать свое p. I'm sorry for speaking Russian for so long, but maybe it was better understandable. I don't know. So let me go to a bipartite graph, yes? What it is. An ordinary picture for a bipartite graph is as follows. Oh, it's a very famous picture of a bipartite graph. Maybe you recognize it or not. Please show me your hands if you recognize this picture. Not everyone, but this is an introductory lecture, so I'll remind you about it, of course. So not everyone knows. Okay, you see, there is one part here consisting of 3 vertices, and there is one part here consisting of the same number of vertices, and here all possible edges going from one part to the second one are drawn. This is not necessary for a bipartite graph. Of course, if we don't draw, for example, this edge, this is also a bipartite graph, and probably you understand that such a definition of bipartite graph is the same as to have chromatic number equal to 2. Okay? I lost one edge. Ah, yes, I lost one edge. Yeah. Thank you very much. Yes. This is a complete bipartite graph. It is denoted by K3, a classical bipartite graph, which appeared in the question of planarity of the graph. Do you know what's planarity? A graph is called planar if it's possible to put its vertices as points on the plane in such a way that every 2 edges intersect only in the vertices. Here you see a lot of different intersections which are going not through vertices. You see, for example, this intersection is not a vertex. You have only 6 vertices. 3 vertices in this part and 3 vertices in this one. And a lot of different intersections which are somehow disturbing. There was a problem whether it's possible to consider 3 vertices like houses and to consider these 3 vertices like, забыл, как будет колодец. Так? Видимо, я не знаю просто этого слова, мне очень стыдно. Well, unfortunately, I don't know how to say it. But here, water estate. Water estate. So the question was whether it is possible to make roads going from houses to these points in such a way that only here the roads are met, are intersecting. So of course it's possible to try making something like that, then here, yeah. Finally, the solution is not found. So it's possible to prove that this bipartite graph cannot be drawn on the plane in such a way. Every drawing of this graph has some parasitic intersections. Паразитические пересечения. Дурацкие. Do you know some other graphs of this kind, which cannot be drawn on the plane without parasitic intersections? K6, it's a complete graph on 6 vertices, yes? A complete graph on 5 vertices. Doesn't that need such a drawing as well? So K5, complete graph on 5 vertices, also cannot be drawn without parasitic intersections. This one. But for example, K4, complete graph on 4 vertices. Here you see this parasitic intersection, yes, but it can be drawn in a different way. Say, for example, in this way. Oh, now you understand, yes? What's polarity? So this is one of the 2 examples which are not blank. And there exists a very famous criterion by RAIGORODSKII, which says that a graph is not planar, if and only if it contains either something like this or something like this. What I mean by something like? In principle, it's possible to make the following operation. You delete this edge, and instead of it, you draw, for example, these two edges. This is not K33, yes? This is already not a bipartite graph. But absolutely, it's absolutely clear that it is also impossible to draw it. If it is impossible to draw such a graph, then this graph cannot also be drawn. Yes. Well, this is called homeomorphic copy of K33. Here also it's possible to take something like that. For example, this graph is not already a complete graph on 5 vertices, but if you believe me that 5 vertices, complete graph on 5 vertices, K5 cannot be drawn, is not planar, then of course this copy is also not planar. This is a famous criterion of RAIGORODSKII. Just few words about bipartite graphs. But to understand, the bipartite graph is the same as the chromatic number smaller than or equal to 2, yes? Probably you know a criterion of bipartiteness. How to check whether a graph can be colored into 2 colors. Consists only of 2 parts. Between them, some edges are drawn, and inside the parts, no edges. There are no edges. No. Huh? If it is a tree, yes, but not only. Do you remember the chromatic number of a simple cycle? We discussed it. It was 2 in the case of even number of vertices, and it was 3 in the case of odd number of vertices. Maybe you divine now how to formulate a criterion.
Does not contain
Odd cycles, yes. Yes, a graph is bipartite if and only if it doesn't contain odd cycles. It's possible to prove it. I don't want to go into the details. This is very simple. You may consider this assertion as just an exercise. If you want, you may try to prove this assertion. A graph is bipartite if and only if it doesn't contain odd cycles. If it contains odd cycles, of course, it is not bipartite. This is absolutely trivial, yes? But the second part of this equivalence must be proved in some 5 steps. This is not so difficult. Okay, so what I want to say, that here the proof that asymptotically almost surely the chromatic number of a graph is bounded from above by 2 must be by proving that with high probability, with probability tending to 1 as n tends to infinity, random graph doesn't contain odd cycles. Am I understanding? If you have questions, please ask me. You may do it in Russian, since in Zoom, I think only my speeches can be heard. You must have a microphone in order to be heard by those who are in Zoom.
Okay, can you repeat your
Last 2 sentences. In order to prove that asymptotically almost surely high of G is less than or equal to 2, we may prove that with high probability, asymptotically almost surely, the random graph doesn't contain odd cycles. Yes? But in this case, it's even possible to prove that a random graph asymptotically almost surely doesn't contain cycles at all. only odd cycles, but even cycles as well. Мы сейчас докажем, что вообще никаких циклов в этом графе нет. С вероятностью стремимся единицы. Все сейчас понятно, да? Окей, fine. Окей. With this assumption, yes, that p times n tends to 0 as n tends to infinity. Then the set of graphs which are bipartite has measure tending to 1 in terms of probability. Не очень страшно. Множество графов с хроматическим числом не больше двойки, двудольных графов, вот по этой мере имеет вероятность близкую к единице. Просто числа вершин. Not too difficult words. Okay? Alive? Okay, fine.
Maybe not simple why we make this
Uh,
what is the function?
No. You see how the situation is being developed. In the first item, I proved that asymptotically almost surely the chromatic number is equal to 1. This is an assumption which is not only sufficient, but also necessary for the chromatic number to be less than or equal to 2. I have to prove it, and I'll do it now. But if you want to understand what will happen in the third item, and there will be a third item, you probably divide. Is the chromatic number less than or equal to 3? So I just invent in some sense these conditions, and I show that they are boundary conditions for having chromatic number 1, chromatic number 2, chromatic number 3. Threshold, пороговый. Second, in principle, on the presentation, everything is written down, but I think it will be not understandable for all of you, so I'll try to do it also on the whiteboard. Okay, what is the probability for a graph to contain a cycle? Let me write down it here. The probability that a random graph contains a cycle. What can be a length of this cycle?
Less than the number of vertices.
Less than the number of vertices, but for example, may it be equal to 1. The number of vertices in a cycle. Yes, the loops are forbidden. Get is optional. So, of course, there are no cycles of length 1. There are no also cycles of length 2, since there are no multiple edges. We have simple graphs. So the number of vertices in a cycle varies from 3 to n. N is the number of vertices of G. So of course it's possible to bound it from above by the sum over all possible keys from 3 to n of the probabilities that G contains a cycle of length k. Contains a cycle of length k. Do you understand this upper bound? I represent this set of graphs containing some cycle as a union of such sets. And then, of course, the probability of a union is bounded from above by the sum of the probabilities of the parts of the sum. Повторить по-русски или понятно? So how to calculate the probability that a graph G contains a cycle of length k? Yes. since the probability of a union does not equal the sum of the probabilities of the parts. The parts are intersecting. For example, you consider the set of vertices consisting of n edges. Do you know how it is called? Someone. Sardelka, да, sausage. And you consider a cycle of length k here, and a cycle of length k here. And of course, a set of graphs containing this cycle as a part, and a set of graphs containing this cycle as a part, they are intersecting exactly by those and only those graphs which contain both these cycles. Here, the probability is the probability of the union of all possible such sets of graphs. But the sets are intersecting, as I've shown here in this picture. Of course, the probability of a union of intersecting sets is not equal to the probability, to the sum of probabilities. You know, inclusion and exclusion formula. Включение. I don't want to write it down since it's very cumbersome, очень громоздкое. But this upper bound is, of course, working every time. The cardinality of a union is bounded from above by the sum of the cardinalities, and the same is true for the probability, of course. Okay, once again, what is the probability of G to contain a cycle of length k? The same thing. It's impossible to say it's exactly equal to something. It's possible to bound it from above by using the same union bound. Ну, то так, вероятность объединений больше, чем сумма вероятностей. What is the union here? Какое здесь объединение? Что мы объединяем? All possible sets of graphs containing concrete cycles on k vertices. How many such sets do we have? How many sets of graphs containing concrete cycles on k vertices do we have? And choose k, of course. For this cycle on k vertices, we have a specific set of graphs containing this cycle. For this cycle on k vertices, we also have a set of graphs containing exactly this cycle and maybe some others. So here we again have an upper bound of the form. Okay, you can see it also on the presentation. But I started to write it down on the whiteboard, so I'll do it. N choose k, we already understood it. What is N choose k? But here on the presentation, you also see k minus 1 factorial over 2. What it is? What is k minus 1 factorial over 2 here? It's also an introductory question in graph theory. Yes, it's a number of possible ways of enumerating vertices in a cycle. If you fix k vertices, you've not yet fixed the cycle. You remember the first example, 1, 2, 3, 4 is not the same as 1, 3, 2, 4. Both cycles have the same sets of the same set of vertices, but they are different. So it's possible to enumerate in different ways the vertices of a cycle. If we even fix k vertices, we can enumerate them in a cyclic order in these many number of times. Why? Okay, let's for example consider vertices starting from 1 and going to k. Yes? And then consider this permutation. K and here 1. Do you understand? These are the same cycles, but different permutations. And so on, k times. But also it's possible to consider this way of numbering the vertices from this set, and also k times. So k factorial, which is the number of permutations, must be divided by 2 times k. And this is, of course, this fraction. Понятно? Repeat what? No, I'm saying that the total number of permutations is, of course, k factorial. You, of course, know, yes? The total number of permutations on k vertices is k factorial. But these k factorial permutations may be grouped. Here is a group consisting of 2k, 2 times k, different permutations, which lead to the same cycle. All these 2k permutations give the same cycle since we don't have orientation. And that's why the total number of cyclic orderings is k factorial over 2k. We just divide k factorial permutations into groups consisting of 2k equivalent cycles. So this is the same number here. And finally, the probability for a graph to contain exactly these k edges, is of course equal to p to the k. Какая двойка? Направления у нас нет, ориентации нет. Поэтому группа состоит не из k перестановок циклических, а из 2k. Once again, do you understand why I just written down here p to the k? What is p to the k? It's the probability of simultaneously containing these k edges of the concrete cycle. We have fixed a concrete cycle. We have chosen k vertices, then we have chosen a concrete cycle, and now we just calculate the probability of obtaining it in a random graph. Yes, and so we multiply it by 1. Ну, мы можем иметь другие ребра, а можем не иметь, поэтому здесь просто умножается на единицу. Мы просто проверяем, что вот эти k ребра присутствуют, а на других хоть трава не расти. Забиваем. Вероятность того, что они есть или нет, их она равна единице. Okay. So I've proven this formula. Now, what is necessary to understand also is that the binomial coefficient n choose k is of course equal to n factorial over k factorial n minus k factorial. I suppose you know it. Yes? The formula for a binomial coefficient. And now I can divide n factorial by n minus k factorial, getting n times n minus 1 and so on, n minus k plus 1, k factors in the numerator, and k factorial remains in the denominator, yes? Every factor here in the numerator is less than or equal to n. Is bounded from above by n. And the number of factors is k. So this is of course smaller than or equal to n to the k over k factorial. Yes? Am I right? Ooh. So we multiply this by this. And strictly smaller than n to the k. When we multiply this by this is of course strictly smaller than n to the power k. So this is smaller than or equal to or strictly smaller than the sum from k equal to 3 to k equal to n and p to the k or k. Let's look at the presentation. Huh? You see the same? You know how to sum up a geometric progression. I preferred here to sum up an infinite geometric progression. A formula is a bit smaller, just for this reason. So if you replace the bound n for k by infinity, and just look at our property, and p goes to 0. So in p it's at least smaller than 1. It's possible to sum up an infinite geometric progression with such, how it is called, NP. Геометрическая прогрессия со знаменателем, да? I don't know. No, знаменатель NP. Okay, so it's of course smaller than or equal to NP cubed. This is the first value of this geometric progression over 1 minus NP. And NP goes to 0, so the denominator goes to 1 and the numerator goes to 0. So we have bounded from above the probability of containing a cycle by something which goes to 0. So the probability that the graph doesn't contain cycles tends to 1 and then tends to infinity. And so the graph can be colored by two colors. Повторить по-русски что-нибудь? Нет, мне самому как бы проще. Если что-то непонятно, я готов еще и по-русски поговорить. Мы оценили вероятность того, что в графе нет циклов. Но мы как ее оценили? Мы сначала оценили вероятность противоположного события, что в графе есть цикл, и доказали, что она с запасом стремится к нулю. Ну, значит, вероятность того, что в графе нет циклов, отрицательное событие, стремится к единице. Ну, а если в нем нет циклов, значит, тем более его хроматическое число равно двойке. Потому что нам было достаточно, чтобы не было нечетных циклов, а мы доказали больше никаких циклов. Окей. Я вас кокнул тем, что много доказываю, но для того, чтобы понять, надо все-таки доказывать. In order to understand, it's better to prove at least something. I don't want to prove a lot, so the third item here is not under a proof. I don't want to go into the details. It's possible to calculate also a bound for this probability, but here you see a boundary condition, a threshold condition for the chromatic number of a graph to be less than or equal to 3. So if P, the probability of an edge, once again, P это вероятность ребра. Каждое отдельное ребро возникает с вероятностью P. If P is equal to a constant over N, it is not little o of 1 over N as this case, in the previous case. But now it is equal to a constant over N. But it's important to see that C, the constant, is smaller than 1 strictly. This is absolutely important here. In this case, it's possible to prove that all connected components of the graph are only trees or unicyclic components. What do I mean by a unicyclic component? With just exactly one cycle, yes. So a connected graph which has exactly one cycle is called a unicyclic graph. It's a tree to which just one additional edge is drawn. Or otherwise, it can be said in the way that it's a connected graph on vertices having exactly n edges. A tree is a connected graph on vertices which has exactly n minus 1 edges. Do you know this? A tree is a connected acyclic graph, but an equivalent definition for a tree that it is connected and it has n vertices and n minus 1 edges. Дерево на n вершинах обязательно содержит только одно ребро. Представьте себе дерево, и вы убедитесь в этом, хотя это надо формально доказывать. This equivalence must also be proven formally, but intuitively it's absolutely understandable if you look at the picture of a tree, not the one which is outside this window, but of a graphic tree. Then you understand, of course, that the number of edges must be smaller than the number of vertices exactly by 1. And in a unicyclic component, we have the same number of vertices and edges. This is a simplest, how to say, extension of the notion of a tree. We just add one edge to a tree, and we obtain a unicyclic graph. It's possible to prove that in this regime, almost all graphs consist only of trees and unicyclic components. Понятно сказал, да? То есть все вот эти компоненты связаны, это только деревья и цилический граф. One more introductory question for those who want to understand what graph theory is. I already spoken about trees. Even two different equivalent definitions have given. Do you know how many different trees can be drawn on n vertices? The total number of graphs is 2 to the power n plus 2, yes? And what is the total number of trees on n vertices? Don't know. It's very important. It's a famous formula of 19th century. No. No one knows. Oh. It's called Kelly formula. Formula Kelly. No. This also doesn't help you. Слышали, да, не помните. Oh, yes, this is also very important. Of course, I'll remind you. So the number of trees on n vertices is equal to n to the power n minus 2. This is called Kelly formula. It's not trivial, you see. In principle, it's possible to divide in some sense. If you consider n equal to 2, you just have one tree on two vertices, and 2 to the power 0 is exactly equal to 1. If you consider n equal to 3, then on 3 vertices, it's possible to draw such a tree. And how many such trees do exist? 3, of course. It depends on the number of these intrinsic vertex. So the number is here 3, and this is of course equal to this value. And finally, if n is equal to 4, there exist 2 different ways, non-isomorphic ways of drawing a tree on 4 vertices. This is a path, say, bamboo. And this one is a star, maybe. But have you seen this bamboo? No. Okay, n is equal to 4. Then we have 2 different ways of drawing a tree. This is bamboo, and this is a star. How many bamboos do you have? Pass. Once again, like in the case of cycles, you have 24 different permutations of 4 vertices, yes?
Divided by 4, yes.
Divided by how many? Divided by 2. Only this is not a cyclic way of ordering. So you just divide it by 2. You may write it 1, 2, 3, 4, and 4, 3, 2, 1. 2 different ways. So 24 divided by 2 is 12. And here the number depends of this intrinsic vertex. So this is of course 4. The sum is 16. And this is 4 to the power 4 minus 2. I'd like to say you this is the proof. It's how to say it, non-complete induction. Неполная индукция, знаете, такое выражение, non-complete induction. So of course it's possible to prove it, and this is also a very, very nice proof, but probably I don't have time, at least right now, today, to do it. If you ask me, of course I can do it tomorrow. But right now, just I remind you this formula. and it's really true. So, okay. So probably, I don't know, probably I have to stop here. 5 minutes more. Okay, 5 minutes more. Okay, very good. Let me remind you during these 5 minutes one more important problem concerning the chromatic numbers. Since I spoke about some problems connected by an edge, in the case of a computer cannot solve both problems simultaneously, yes? But I didn't speak about the classical problem concerning the chromatic number. And I heard from the audience that someone or some people from the audience spoke about this problem. And I didn't speak about it, so I have to speak about it right now, just for 4 minutes now. A famous current problem. From this famous current problem, in fact, the chromatic number appeared. Вот само понятие хроматического числа возникло благодаря этой задаче. Yes, of course, 4-color problem. Classical 4-color problem. You have a map of the world. You have some countries. This is a good country. This is a little bit worse one. All right. Oh. It's a bad country, but it also may exist on our map. So the only condition here is to not have enclaves. Не должна быть страна внутри страны и не должно быть несвязанных стран. And also a common part of a border must be a continuous line. Не одна точка, not just one point. Continuous line. A lot of such countries, maybe a billion of such countries, or I don't know, a Google. Do you know this word? Google. Yandex. What are we doing with such map? Of course, we are trying to cover different countries in such a way that if two countries have the same border, share a border, then of course they must be colored into different colors. And we want to use the minimum possible number of colors in this color. The conjecture which was proposed in the middle of 19th century was that 4 colors every time is sufficient. It's possible to color any such map into 4 colors. It's not a practical problem, of course, since it's not very important for real cartography to have so small number of colors. Ну, кто старается минимизировать, знаете, вот Африку покрасить в 4 цвета, ну, можно, конечно. It's possible to color Africa into 4 colors, but this is not very practical. It's not very important, but this is a beautiful problem which was completely solved only in 1976 when this problem was reduced to the consideration of about 1,500 different cases. Проблема была сведена к рассмотрению порядка 1500 случаев. And all these cases were verified on a computer. This is not so beautiful already, but during 130 years of the existence of this problem before it was solved, a lot of different, a tremendous amount of different notions in graph theory appear, including, of course, chromatic numbers and chromatic polynomials. So this is once again an illustration for my favorite principle. Mathematics is not beautiful because it has applications, but it has applications because it is beautiful. Не потому математика прекрасна, что у нее есть приложение. У нее есть приложение, потому что она прекрасна. Вот появляется красивая задача, фигня какая-то, а потом выясняется, что куча приложений. Okay, people, thank you very much for your attention. Let's continue tomorrow.